Imitation learning is a simple and stable approach to robotic learning. However, it has one major shortcoming. It requires expert operators for data collection, which makes it difficult to scale to large datasets. Scaling to large datasets would enable learning-based robotic systems to generalize broadly to new tasks and objects. Typical imitation learning involves collecting expert demonstrations independently for each task. Meta-imitation learning alleviates the data collection problem to some extent by sharing data across many different tasks, but does not allow for autonomous data collection. Reinforcement learning, in comparison, allows for autonomous data collection but requires task-specific reward functions and is notorious for being a difficult optimization problem. We propose scaling imitation learning to large datasets via adopting a multitask perspective and leveraging autonomous data collection. We make the following key insight. Trials that fail for one task could prove to be successes for other tasks. We learn a latent space of tasks to autonomously organize collected trials into new tasks. Here is a visual overview of our approach. We bootstrap a meta policy using meta-imitation learning and use it for collecting trials in new environments. We use the same initially provided multitask imitation dataset to learn an embedding network that maps each demonstration or trial into a task vector. The collected trials are then autonomously organized into tasks based on the similarity in the learned latent space, and these tasks are added to the imitation learning dataset. Here is the neural network architecture used to represent our meta policy. It uses convolutional neural network to process images and uses 1D convolutions to pool temporal information from demonstrations and trials. We consider a challenging domain involving hundreds of tasks and almost 100 different kitchenware objects. We evaluate our method on a one-shot adaptation setting. We provide a single demonstration of how a task is to be performed and then ask the policy to perform the same task in a different setting. We bootstrap our meta policy using 800 demonstrations collected using a virtual reality interface and collect 60,000 trials autonomously. We compare our method to both meta-imitation and behavior cloning. We see that our policy significantly outperforms meta-imitation learning, a state-of-the-art approach for one-shot imitation. Our initial meta policy produces reasonable behavior but cannot utilize trial data and is not able to succeed on all tasks. We collect thousands of trials using this policy and use them for updating the policy. The new policy makes use of these trials and is able to achieve a higher success rate.